You've probably heard the news. NASA just peered deeper into the early universe than ever before, and they saw something that should make physicists very uncomfortable. But this is where physics gets strange. What NASA found wasn't just another distant galaxy. It was a direct contradiction to our models of the early universe, a complete breakdown of the physics we thought we understood. Let me be blunt, the observations don't fit the theory at all. And that's a big problem, because for decades we've been telling a very tidy story about the origins of the cosmos, a story that now has a gaping plot hole. So what exactly did NASA see that was so disturbing? I'll give you a hint. It wasn't more of the same. Quite the opposite. They saw structures and objects that simply shouldn't exist according to our current understanding. Some things that require us to rethink some fundamental assumptions. And that's really the core issue here. When observations clash this dramatically with theory, it's not just an anomaly. It's a sign that the foundations of the theory itself may be flawed, that we've been starting from the wrong premises all along. But to understand why this NASA finding is so unsettling, we need to go back to the beginning. Not the beginning of the universe, but the beginning of our theory about the universe. The Big Bang model. For nearly a century, the Big Bang has been the dominant framework for understanding the origins and evolution of the cosmos. It's a compelling story, an expanding universe growing from an initial singularity, cooling and coalescing into the structures we see today. Elegant, logical, satisfying. There's just one problem. The real universe didn't get the memo. It's far more unruly and unpredictable than our tidy Big Bang story allows. And these new observations are a stark reminder of that fact. What they don't tell you about the Big Bang model is that it's not really a complete theory. It's more of a rough sketch with a lot of details left to be filled in. And as we've started to color in those details with actual data, the picture has gotten increasingly messy. But this NASA finding isn't just adding to the mess. It's revealing a fundamental flaw in the sketch itself, a flaw that goes all the way down to the quantum level. You see, the early universe wasn't just hot and dense. It was a seething cauldron of quantum fluctuations, a place where classical notions of space and time break down entirely, where the very fabric of reality is constantly churning and rearranging itself. And that's really the core of the problem. We've been trying to understand the quantum origins of the universe using theories that are fundamentally classical in nature. Theories that simply can't capture the true strangeness and complexity of quantum reality. But as unsettling as this realization may be, it's also an incredible opportunity, a chance to build a new framework for cosmology that embraces the quantum weirdness of the early universe rather than papering over it. And that's where the real work begins. To construct that framework, we'll need to dig deep into some of the most challenging and counterintuitive areas of physics, quantum gravity, information theory, the holographic principle. Before we go any deeper, I need to ask you something. If you're here for comfort, this isn't the channel for you. But if you're here for truth, even when it's unsettling, take a second to support this mission. Hit like, subscribe, and leave a comment telling me what part of reality shocked you most. Every interaction tells the algorithm that depth matters more than distraction, and that thinking clearly still has value. If you want to keep tearing apart reality with me, episode after episode, make sure you're following. We're just getting started. We'll need to question everything we thought we knew about the nature of space and time, and be willing to abandon cherished assumptions that no longer fit the data. But if we can rise to that challenge, the payoff will be extraordinary. A true theory of quantum cosmology, one that can account for the strange and wondrous complexity of the universe we actually observe. It won't be easy. It will require us to grapple with ideas that seem almost impossible to visualize or intuit. But as physicists, that's exactly what we signed up for. Because at the end of the day, physics isn't about telling comforting stories or preserving familiar ways of thinking. It's about you following the evidence wherever it leads, even if that means venturing into strange and unfamiliar territory. And that's exactly what NASA has just forced us to do, to confront the quantum strangeness of the early universe head on, and to build a new cosmology that can finally make sense of it. So buckle up, because the real journey is just beginning, and it's going to take us to some very strange and wonderful places. We just saw how NASA's observations have shaken the foundations of classical cosmology. But buckle up, because we're about to dive into the quantum realm, and that's where things get really wild. You see, the early universe wasn't just hot and dense. It was a seething cauldron of quantum chaos, where the very fabric of space and time lost all meaning, a place where our classical intuition breaks down entirely. But to understand why, we need to start with a concept you might think you already know: entropy. Most people think of entropy as a measure of disorder, but there's a deeper way to think about it, as a measure of lost information. Every time a system evolves according to the laws of physics, information is lost. Quantum possibilities collapse into classical realities, and the rich tapestry of what could be fades into the stark certainty of what is. And that's really the arrow of time in a nutshell. The inexorable flow from the quantum to the classical, from the possible to the actual, from high entropy to low entropy. But in the early universe, that arrow gets thrown for a loop, because in the first fractions of a second after the Big Bang, entropy was almost unimaginably high. And as the universe expanded and cooled, all that entropy had to go somewhere. Now, some of it leaked away as heat and light. But what they don't tell you is that a huge amount of that primordial entropy is still lurking in the quantum fields that fill the vacuum of space. And this is where the classical picture starts to unravel. Because according to quantum field theory, the vacuum isn't empty at all. It's a roiling sea of virtual particles constantly popping in and out of existence. But if you think that's strange, just wait, because it gets even more bizarre. These quantum fields aren't just a backdrop. They're the lead actors in the cosmic drama. They can warp the stage of space-time itself, bending it and twisting it into the illusion of gravity and curvature. In other words, space-time as we know it may be nothing more than a hologram, a projection of the deeper, truer reality of the quantum realm, a shadow on the wall of Plato's cave. And that brings us back to those NASA observations, because what they saw in the whispers of the early universe were the echoes of this quantum chaos. Tiny fluctuations and anomalies that simply shouldn't exist in the classical picture. A ghost images of a reality that's far stranger and more malleable than we ever imagined. A reality in which information is the currency of existence, and the laws of physics are just the rules of the game. But if the early universe was a wild west of quantum anarchy, how did it give rise to the orderly, predictable cosmos we inhabit today? How did entropy wind up so low, in defiance of the second law of thermodynamics? The answer may lie in a mind-bending idea called the holographic principle. The notion that the information in any volume of space can be fully encoded on its surface, like a cosmic barcode. Applied to the early universe, the holographic principle suggests something astonishing: that the apparent disorder of the quantum realm may have been a trick of perspective, a holographic projection of a deeper, simpler reality. A reality built from qubits, the fundamental units of quantum information, woven into the very warp and weft of spacetime. A hidden code written in the language of entanglement and superposition. But to crack that code, we'll need to plunge even further down the quantum rabbit hole, into a wonderland of ideas like the ER equals EPR conjecture, the black hole information paradox, and the firewall debate. Ideas that will shatter your classical intuition and rebuild it anew, quantum brick by quantum brick. And that's exactly what we'll do in part 3. We'll see how the union of holography, information theory, and quantum gravity is forging a new conception of space-time itself, a conception in which the cosmos is a living, breathing, evolving network of quantum information. A strange new world, to be sure, but one that just might hold the key to the deepest mysteries of existence. So gird your mental loins, dear viewer, because we're about to leave the familiar shores of classical thought behind and set sail for the uncharted waters of the quantum realm. It won't be a comfortable journey. Your cherished beliefs will be challenged. Your intuition will be turned inside out. But if you're brave enough to weather the storm, I promise you this: the view from the summit will change the way you see reality forever, and you'll never look at a vacuum the same way again. You've probably heard that information can never be lost in the universe, that every bit and byte, every qubit and photon is secretly preserved in the cosmic ledger. But what they don't tell you is that this seemingly innocent idea has been quietly detonating like a bomb at the foundations of physics. And nowhere is the fallout more spectacular than in the bizarre realm of black holes. You see, black holes have a dirty little secret. Stephen Hawking showed long ago that they're not really black at all. They actually emit radiation, slowly leaking information back into the universe like a punctured balloon. But here's the rub. If information can escape from a black hole, that means it wasn't really lost in the first place. And if it wasn't lost, then where the hell was it hiding all this time? This is the black hole information paradox. And for decades, it's been driving physicists to the brink of madness, because it seems to pit two of our most cherished theories against each other in a battle to the death. On one side, we have quantum mechanics with its ironclad guarantee that information is always preserved. On the other, we have Einstein's general relativity, which says that anything that crosses a black hole's event horizon is gone for good. So, who's right? Well, buckle up, because the answer may blow your mind. In the 1990s, Leonard Susskind and Gerard 't Hooft proposed a seemingly crazy idea. What if the information that falls into a black hole isn't lost, but just scrambled and smeared across the event horizon like some kind of cosmic graffiti? In other words, what if a black hole's surface area is a direct measure of its information content, like a holographic hard drive etched in the warped geometry of space-time itself? This is the holographic principle. And it's not just some wild speculation. It's a mathematically precise statement about the nature of quantum gravity. A statement that's been borne out time and again in the esoteric calculations of string theory and ADS/CFT correspondence. But if the holographic principle is right, then everything we thought we knew about space and time gets turned on its head. Because it means that the true arena of reality isn't the three-dimensional stage we see around us. It's the two-dimensional boundary that surrounds it. In other words, reality is a hologram, a cosmic projection, flickering on the screen of the universe's event horizon. And that's not even the strangest part, because if space and time are just a hologram, then what does that say about the supposed firewall at the edge of a black hole? How can information be both smeared across the horizon and lost forever in the singularity? The answer, according to Susskind and others, is that it can't. The firewall paradox is an illusion born of our stubborn clinging to classical notions of locality and causality. In the quantum world, information doesn't just sit in one place. It's smeared out and entangled across vast distances. It's non-local, in the jargon of physics. And that means that the bits that fall into a black hole are fundamentally connected to the bits that radiate back out. This is the essence of the ER equals EPR conjecture, proposed by Susskind and Juan Maldacena in 2013. The idea that entangled particles are connected by tiny wormholes, Einstein-Rosen bridges, in the language of general relativity. In other words, the geometry of space-time itself is stitched together by the threads of quantum entanglement. The universe is a vast, interconnected web of information, with black holes as the ultimate nodes in the network. And this, my friends, is where the real mindfuck begins. Because if ER equals EPR is right, then the holographic principle isn't just a mathematical curiosity. It's a fundamental feature of reality itself. It means that the three-dimensional world we see around us is just a shadow, a projection of a deeper, two-dimensional reality. A reality where space and time are emergent properties, born of the intricate dance of quantum information on the boundary. And it gets even weirder, because in this holographic universe, the cosmic story isn't just written in the stars, it's written in the entanglement entropy of the vacuum itself. Every fluctuation, every ripple in the quantum foam encodes a vast amount of hidden information. Information about the birth of the universe, the fate of black holes, and perhaps even the ultimate nature of reality itself. And the only way to read that cosmic script is to embrace the utter strangeness of the quantum realm, to let go of our classical intuitions and follow the equations into the abyss. It won't be a comfortable journey. Your mind will be bent, your reality will be warped, and your very notion of what it means to exist will be challenged to the core. But that, my fellow travelers in the strange, is the price of admission to the universe's most exclusive club. the club of those who have glimpsed the true face of reality in all its bizarre, holographic glory. So what do you say? Are you ready to take the red pill and see just how deep the rabbit hole goes? Are you brave enough to stake your sanity on the cutting edge of theoretical physics? If so, then welcome to the strange new world of quantum gravity, black hole firewalls, and holographic universes. It's a world where nothing is what it seems, and everything is connected in ways that defy the very notion of space and time. But it's also a world of unparalleled beauty and mystery, a world where the very fabric of reality is woven from the gossamer threads of pure information. And who knows, maybe, just maybe, it's a world where we'll finally find the answers we've been seeking since the dawn of human curiosity. The answers to the deepest questions of existence itself. So buckle up, my fellow explorers of the unknown, and let's see just how far the holographic rabbit hole can take us. If your mind has been blown and your reality has been forever altered, then I've done my job. The universe is a wild, weird, and endlessly fascinating place. And the more we probe its secrets, the stranger and more wonderful it seems to become. So keep asking the big questions, keep exploring the boundaries of the possible, and above all, keep sharing in the grand cosmic adventure that is science. Until next time, stay curious, stay wild, and never stop wondering at the mystery of it all.